Hello, everybody. Welcome back to Markov Processes. Not too long ago, I put up an announcement on the Canvas page giving some clarification on a couple of problems. So check that out. It's basically in problem 5 where you have to explain something as a Markov chain. You don't have to prove it. It's just saying, just explain it in English. And in problem 4, there is a double sum, and you can assume that you can interchange the order of the sum. Don't worry about that for now. And one that I wanted to talk about before we got going was problem 3, because I think that's throwing the most people with the indicator stuff. So in problem 3, we have it is 3. We have 4 balls randomly distributed into 3 boxes, and we want to know the expected number of empty boxes. So I've got like box 1, box 2, and box 3. And then I have 4 balls that are going to be distributed into each box. And so I just wanted to say something about the indicator random variable. I put an indicator random variable into this problem, I sub I, and this is defined to be 1 if the ith box is empty and 0 otherwise. I don't know if that seems backwards to you because it's empty, and shouldn't that be the 0? But really, I'm trying to figure out when boxes are empty, so I want something that's going to indicate that to me and turn on. So then the number of empty boxes is I1 plus I2 plus I3. And the expected number of empty boxes is the expected value of this sum. And expectation is a nice linear operator, so you get to run that through. And here's where it gets a little weird. I don't think it's weird, but I understand if it feels a little weird. We need to compute these expectations, and there's nothing special about which box has which number on it. So this is actually going to be 3 times the expected value for, say, box 1. There's just no reason to expect anything different because they're being randomly distributed. So let's talk about that expectation. Let's look at the expected value of I1. So this is a 0 or 1 discrete random variable, and it is going to be 0 times the probability. This expectation is going to be 0 times the probability it's 0 plus 1 times the probability it's 1. And so we're just left with the probability that the indicator for box 1 is 1. But given what it's indicating, it's only going to be 1 if the box is empty. So this is the probability that box 1 is empty. So we've got, I'm going to go back to my picture. We've got these 3 boxes and 4 balls. And if we're going to just focus on box 1, if we're starting to randomly put the balls in boxes, each of these balls has probability 1/3 of ending up in box 1. And when we're distributing them, we have 4 trials to get balls in box 1. And I know that feels weird to not consider the other boxes, but because of the linearity of the expectation, we don't have to do it. So the number of balls in box 1 or any box it's a binomial random variable because that counts the number of successes in n trials of an experiment. So I'll just remind you really quick, but it's going to be binomial. We have 4 tries and success probability 1/3. So little p is the probability of success for any one ball. Success means you get into box 1, and that's going to be 1/3 of the time. And n equals 4 is the number of trials to get those successes. So again, I think it feels really strange not to consider the other boxes. And you would have to consider the other boxes if the question were different, maybe asking you something that is not so nice and linear as the expectation. But yeah, this is all you need to do. By the way, the homework is intended to always cover the week before. So I know we don't have class this Monday. We have a hard-earned vacation coming up. But your Wednesday homework is never supposed to cover the Monday just before. And if I don't get through everything I wanted to by Friday's lectures, I may cut problems out and move them to the next assignment. But, oops, I don't want to go there. We are ready to do some actual numerical computations. And I want to start off with a ridiculously oversimplified model of the weather. So on each and every day, the weather can either be sunny or rainy. So it's oversimplified there for sure. Can it be cloudy? Can it rain for half the day? You know, there's no such thing. It's just a simplified model. And the weather is thought to behave like a Markov chain. And that, of course, is another simplification because there are weather patterns and weather fronts, right? And when weather comes in, maybe the weather today is dependent on several days of weather. So this is oversimplified, but it's just a starter example for us. So I'm going to let xn be the weather on day n. And this is my bold P. Now, that's really weird looking, but I'm assuming it has this as its probability transition matrix. So the probability you go from sunny to sunny on any given day is 0.8. The probability you go, say, from rainy to sunny on any given day is 0.3. And that's kind of just where we got last time, but I want us to try to answer some questions here. Okay, get rid of this. So I have a bunch of questions, and this is very similar to the homework problem 6. So my first question is, what is the probability? Oh, by the way, I'm going to write things like this. Let me write this line. What is the probability that on day 1 it is sunny, given on day 0, like the starting part of this experiment, it is rainy? A caveat, random variables are supposed to be numerical and real valued. And we can certainly fix that by like renaming sunny and rainy to 1 and 2 or 5 and 18. No one cares. But I think it's a lot easier to see what's going on in all of the questions we're going to do by just putting the letters in there. So technically, random variables should be numeric. But feel free to go ahead and do it this way in this course. Okay, so this is going from rainy to sunny in one time step. And that means we just grab the rainy to sunny entry. So this is going to be 0.3. My next question here is, what is the probability that x18 is sunny given x17 is rainy? And the point of this is that if you're given a Markov chain with a transition probability matrix, that matrix is not going to make sense if it's not time homogeneous, because this matrix is supposed to represent the probabilities of moving from sunny to sunny and sunny to rainy over every or any one given day. And so if those probabilities are going to change based on what day we're looking at, then it's not time homogeneous. Also, I said last time, just assume that it will almost always be that until towards the end of the course. So I got a question about knowing which numbers correlate with x1 and x0 in the table. So looking back at my first probability, we are moving, for number 1, we're moving from rainy to sunny, rainy at time 0 and sunny at time 1. So I went from rainy to sunny and got the 0.3. And in this second problem, because we're assuming time homogeneity, it's still a one time step transition. So this is again going to be 0.3. Okay, so I've got another question for you. Third up, what is the probability that x18 is sunny given x17 is sunny and x16 is rainy. So now you just want to use the Markov property. If you're given some history of the chain, only the most current value is relevant to the calculation. So I can drop this part. I'm going to put an MP up here. That stands for Markov property. And now I just have a single time step going from time 17 to time 18. Single time step transition. I want to look at the matrix and go from sunny to sunny. And that number is right up here. So the answer to this is 0.8. Yeah, it's fine if you just leave it like this. But yeah, another way to do this would be to say x18 is sunny given x17 is rainy. You can do something like where you say, you don't have to do this, that's what I just said, the time homogeneity. This is the probability that x1 is sunny given x17, sorry, x0 is rainy. And then you can go on and answer it from there if you really want to write that. Okay, yeah, so 1, 2, 3, 4. For my fourth trick, bring the matrix back down. Let's look at the probability that, so this is going to be a joint probability with nothing conditional. The probability that x0 is sunny, so sunny on the starting day, x1 is sunny, and x2 is rainy. And as it stands, we can't answer this. And the reason we can't answer it as it stands is that we only have this probability transition matrix. We only know about transitioning. So if we knew where we started at time 0, if that was given on the right side of a given line, then this would be something we can do. So we're going to need to solve this problem a so-called initial distribution. So if someone's not going to tell us where we are at time 0, they can at least give us maybe the probability it's sunny versus rainy. And so let me put a colon here. The probability that maybe x0 is sunny, I'm going to call this some parameter, lowercase p. And the probability it's rainy will be the rest of the probability, 1 minus p. And once you have that, then we can answer this. So let's try it. Here is the goal. x0 is sunny. x1 is sunny. x2 is rainy. The transition matrix gives us conditional probabilities. So let's make this look conditional. And we do know that we kind of know things about the latest time step. So for that reason, I'm going to write this as the probability that x2 is rainy given x1 is sunny and x0 is sunny times the probability that x1 is sunny and x0 is sunny. So that's me unraveling the definition of conditional probability and kind of having this be like an event A, intersected with an event B, and using the fact that the probability of A intersect B is the probability of A given B times the probability of B. Okay, so at this point, in the first conditional probability there, we can get rid of this by the Markov property, because where we are at time 2, if we know where we are at time 1, the history further back doesn't matter. But I still have to deal with this, and I want to turn that into a conditional probability as well. So this is x2 equals r given x1 equals s. I'm going to write the x0. Just I'm going to delete that or cancel that out at the very end, so you can tell what piece went with what piece. But I can write that probability as x1 is s given x0 is s. times the probability x0 is S. And again, this can go by the Markov property. And now I'm looking at the probability x0 is S that was given to be P. And this is a one-time step transition from sunny to sunny. I think that was 0.8. Yeah, that was 0.8. And then here I have a one-time step transition from sunny to rainy. And that's the 0.2 up here. So that is the answer. It's a little weird to have numerical stuff on part of it and not the rest. Okay, so the main point of all of that was if you have to find a probability of just an intersection with nothing conditional, then someone needs to tell you how you're starting the chain, and then you can condition on that. Okay, I have two more, I think. So we are on E. What is the probability that X1 is rainy? So again, there's no transition here, but we can use the law of total probability. The probability that X1 is rainy, or, I don't really call it that law of total probability in Markov processes. I call it conditioning on where we are at time 0. So condition on the chain at time 0. And then I can write this out as the probability that X1 is rainy given X0 is rainy times the probability X0 is rainy. And I have to consider all the cases for X0. So then the probability that X1 is rainy given X0 is sunny times the probability that X0 is sunny. Or if you prefer to see it like we wrote it last time, the probability that X1 is rainy, this is going to be the sum of the probability that X1 is rainy given X0 is some state I times the probability X0 is some state I, and then we're summing over all I in the state space so that S can be confused with sunny, but I is sunny or rainy. We have to sum over those two things. Okay, I'm going to use the line above just because everything is sitting right there. And we get the rainy to rainy probability is 0.3. The probability that the chain starts rainy, that's 1 minus P. By the way, I'm assuming the same initial distribution. Otherwise, I would have to be given one because there's nothing conditional here. Plus sunny to rainy, and that was 0.2. And then the probability of sunny on the first day is P. This is wrong. Rainy to rainy is rainy to rainy, or 0.7. Okay, I have a final one, unless please stop me or direct message or message everyone if you have a question. But what am I on? F. Okay, so this is going to be a little different from everything we've done so far. What is the probability that on day 2, it's rainy, given on day 0, it was sunny? So this is I don't want the quotes there. I want the quotes here. This is a 2-step transition. Maybe I do want the quotes on the outside. Okay, so I'm going to do it the long way, which is then going to motivate I don't know if it's actually a shorter way, but you're going to have a preference, I think, for one or the other. The probability that X2 is rainy given X0 is sunny, I only know 1-step transition probabilities, so I need to bring in that X2. So I'm going to condition on X2. This is the probability. I don't know if I didn't do it in the previous example, but one thing I could write here is the sum over I of the probability that X2 equals R and X1 equals I, given X0 equals S. And then I could write that conditional probability. Sorry, I could write this intersection with a conditional probability. So this is going to be the probability that X2 equals R, given X1 is sunny and we stay in the universe where x0 is sunny, and then we multiply by the probability that x1 is sunny, staying in the universe where x0 is sunny. And then we get the same line again, but with x1 being rainy. If you are conditioning on x1, then you usually don't write this out because you have already figured out that that means this is going to happen. So it's just like the previous problem where the probability of x1 being rainy, we conditioned on x0 and multiplied by the probability of x0, and we summed over all the possibilities for x0. So right now we're conditioning on x1, but we are constantly staying in this universe where x0 is given to be s. So it becomes x2 equals r given x1 equals s, staying in this universe, times the probability x1 is equal to s, staying in this universe. And then the same thing for x1 equals rainy. And by the Markov property, I can drop the x0 equals s here. And now I should be able to look these all up. Let me bring the matrix down again, since I screwed that up last time. The first probability goes from sunny to rainy. And so I'm going to look in the matrix at sunny to rainy. And that is 0.2. The next probability, it goes from sunny to sunny. And so that is the sunny to sunny entry. And that is, it was supposed to be color coded. Actually, I'll just underline them because I'm not sure you can read these colors. Everyone can, I'm not sure who has problems with certain colors. So this is 0.2 times 0.8 plus R to R is 0.7. And then S to R is 0.2. And so I'm not going to continue the color coding, but this was the green one, and this was a pink one, and so on. Ooh, do you see anything here? Look at this answer, and look at this matrix. It kind of looks like matrix multiplication happened. If I were to put this matrix 0.8, 0.2, 0.3, and 0.7, like multiply it by itself, then I am going to get, when I take this row times this column, I'm going to get this. And that result is going to end up here in a 2x2 matrix. And so it appears, but we're going to prove it, that if you want to go from one state to another in 2 time steps, you can just look at that entry in the square of the matrix. We're going to prove it now. And if it's 3 time steps, you can cube the matrix. So that's super useful, especially when problems get bigger with more states and the number of things you're conditioning on gets huge. You know, if you want to say, what is the probability that x18 is rainy given x0 is sunny? I certainly don't want to condition on x1 through x17. So I just want to note here that this looks like the sunny to rainy entry of the P matrix squared, which brings us to a very exciting new section in the notes. We're going into section 2.2 now. It's called the Chapman-Kolmogorov equations. We're gonna prove what we just kind of saw. And in excuse me, in order to do it, so I need some new notation here. And I want to talk about multi-time step transition probabilities. So we were using a lowercase p ij to denote the probability of going from I to j in 1 time step before. And now I want to put a superscript of n in parentheses. So if you're looking at the references that I gave links to on the course syllabus page, the first one, the book by Durrett, he actually writes what we're going to define as Pij to the n. And I think that is horrible. That looks like the nth power of Pij. And what we're about to write is definitely not the nth power. So this is going to be our notation for the probability that we transition from I to j in n time steps. And again, it is not the same thing as Pij to the nth power. So sorry for anyone trying to write this, but let me go back to the previous problem. I did not take the S to R entry of the matrix, which is right here, and square it. That's not what happened. So before we state and prove the Chapman-Kolmogorov equations, I just want you to note one thing. This is nice and defined for 0 time steps. So that's supposed to represent the probability you go from I to j in 0 time steps, but you're not allowed to move in 0 time steps. And that means that you're going to still be at I. So this is going to be 1 if j is equal to I, and 0 if j does not equal to I. You're always going to stay at I in 0 time steps. So that's really nice for completeness of some of the algebra coming up. That was a parenthetical, so I'll close that up. Here are the Chapman-Kolmogorov equations. I'm going to write them in 2 ways. There's even more ways you can write them. So the probability of going from I to j in n plus m time steps can be written as the sum over all k in the state space. The probability we go from I to k in m steps, and then we go from k to j in the next n steps. We're going to prove this by conditioning on where we are at time after m steps, and then summing over all the possibilities. But this is just saying, if you want to go from some I to some j in n plus m steps, you can actually look at any time step in there and sort of say, where did I land? And condition on that for any one of the time steps. You don't have to condition on all of them. And another way to write this, I don't like this one as much, but it's totally equivalent. Oh, by the way, this is for all I and j in the state space, and for all non-negative integers n. And another way to write this is to say the probability I go from I to j in n steps is so not having n plus an additional m steps, but just stopping somewhere before the n steps. So it's going to look similar. The sum over k and s of the probability of going from I to k in some m steps, and the probability of going from k to j in the remaining n minus m steps. And this has to hold only for m from 0 up to n. I never liked this one as much. So we need to prove this, and we're about to, but hopefully, I don't know, hopefully that feels a little bit intuitive. If I want to go from I to j in n plus m steps, I could go somewhere in m steps and then get to j in the remaining n steps, and then just kind of sum out where I went, kind of like marginalizing that out. You'll see in the proof. So the probability of going from I to j in n steps is just that. And you do not have to write this first piece. You could go directly to the second piece, but this is the probability. I'm going to start at some time L at state I, and then n plus m steps later be at state j. So like x sub L plus n plus m equals j, given xl equals I. But by time homogeneity, I can just take L to be 0, which is what I want to do. And you could have done that in the first place. You could have totally ignored that step, because by time homogeneity, this is the probability we are at j at time n plus m, given we were at I at time 0. And again, you could just go directly there. And now I'm going to bring in where we are at time m. So here, the huge equal sign, I'm going to condition on where the chain is at time m. So I'm going to have to sum over all possibilities there. This is going to be the sum over all k in the state space. I'm going to let where I am at time m vary over all k in the state space. And then I could write this as a joint probability and then turn it into a conditional, but I'm going to go straight to conditional because we are conditioning on the value of the chain xm. So this is the probability xn plus m equals j given xm equals k times the probability xm equals k. Oops, it's not wrong, but it's bad. I still have x0 equals I up here because I stay in conditional land. It's going to get dropped, but I didn't mean to do that. X0 equals I. And yeah, so now this gets dropped by the Markov property. And so this first guy is the probability of moving from k to j in n time steps, because I started at time m and then looked n time steps later. And so this is probability of going from k to j in m time steps. And this one is, this is an m, sorry, it's a little hard to read. Sorry, that first one should be n time steps, not m. M. Okay, and the other one is the probability of going from I to j in n steps. And that's what we wanted to show. I mean, the order's not right, but well, I don't want to make it so small that you can see Chapman-Kolmogorov again, but we were trying to prove, guys, why didn't anyone tell me this? So here, sorry, I'm trying to blame you for my problems. I was trying to do an n plus m step transition probability. This was supposed to be n plus m steps, not n steps. At least the way I conditioned on it. I could have started with this being an n and saved the problem, but I've already solved the problem the other way. This final subscript j, I'm running out of correction colors, but this should be a k. Oops. Yeah, the upper indices should be flipped as well. And so it doesn't look exactly like the one I stated, but all we would do to make it look the same is in this step, we would condition on where the chain is at time n, not at time m. Like then the indices, then the time steps would be the other way. So really sorry about that. Check it out in the notes where it's written more neatly. I think eventually it's okay, but just starting out, like on your first homework assignment, it will let the graders know that you knew to drop it and didn't just not have it, because it's a common mistake to just, as you're conditioning on another random variable, to kind of lose the original conditional stuff. So I'd ask that you actually show this a couple of times, the first homework or two. Here's what we know. By the way, the second form of, so we proved this kind of, I messed up some of the letters. This is proved in exactly the same way. And now here's what we know. So the Chapman-Kolmogorov equations say that I go from I to j in n plus m steps by summing over all k in the state space, the probability I go from I to k in m or n steps, and the probability I go from k to j in n or m steps, depending on what you put on the first one. And check this out. For like the I and j is kind of fixed here, we want to find the n plus m step transition probability from I to j, and the k is moving. And so this first PIK here this is running in K across the ith row of the transition matrix. And this guy is for a fixed J running down the kth column. And that is matrix multiplication. You know, the ijth entry, when you multiply two matrices, is going to come from the first, the ith row and the jth column, and you multiply all the individuals, and then you add them up. So this actually is the ijth entry of, that's written really bad, of P super M times P super N. And this notation is the ijth entry of P super N plus M. So we've just proven that you can get a multi-step transition matrix by multiplying other multi-step transition matrices. And because I could make this N and this M, I could condition the other way, we can get this in the opposite order as well. So we have, just recap this down here. So similarly, remember when I said I'm going to condition on where we are at time N and then change it to an M? You can do it both ways. We can get that the transition matrix in N plus M time steps is the transition matrix at time N times at time M. So this is telling us that these transition matrices are commutative, which is nice because matrices don't always do that. So check this out, because this is where it's really going to be useful, I think. I just want to note a couple of points of notation here. So this P matrix with a 1 in the parentheses, that is the one-step transition probability matrix. So that's just our original P. And the P matrix with a 0 in parentheses, that's just filled with transition probabilities of going from I to J in 0 units of time. And we said that that's going to be 1 if J is equal to I and 0 otherwise. So this is going to be the, I'm not going to write I because I think it'll look like an indicator or something. This is going to be the identity matrix. Because in 0 time steps, if you're at 1, you stay at 1. So the 1, 1 entry is 1, and the rest of the row is going to be 0 because the rows add up to 1. But with that, check this out. The matrix of two-step transitions, which I really should write here, but I'm running out of time. The matrix of two-step transitions we just showed can be written as the matrix of one-step transitions times the matrix of one-step transitions. And we just realized that that is just the original matrix, P times P. So this is the original matrix squared. Two-step transitions, you can get it by squaring the matrix. The individual probabilities don't work that way. So remember, the individual probability of going from I to J in 2 time steps is not the probability of going from I to J squared, which is why I'm really sad about how Durrett wrote that in his book. I think you can probably see what's going to happen here, but let me write one more. The 3-step transition matrix probability, we can break this up as in a number of ways, well, a couple of ways. So I can do it as the matrix of 2-step transition probabilities times the matrix of 1-step probabilities, but we just saw that that 2-step transition probability matrix is the original 1 squared. And so we get P cubed. And so in general, we have that the matrix of n-step transition probabilities is the original matrix to the nth power, which is going to be really convenient. I mean, at least if you're doing this on a computer or something, if you have a large state space or a large number of time steps that have gone by, because remember what we were trying to answer here, the probability that x2 was rainy given x0 is sunny, you could just compute p squared I'm sorry, I don't have it ready to go. And then you can grab the sunny to rainy entry, and you'll get the same answer we got before. Yay, us. Okay, we are out of time and we are on vacation. I don't know if you have more classes today, but blow them off. Tell them I told you to. Um, yeah, I'll be checking my email over the break. So thank you, and I'll see you next time on Markov processes.